All right, so today is where we really dive in to new information, new concepts for pre-calc, stemming from what we already know about algebra 2 and polynomial functions. So something new here we have is the rational zero test or the rational zero theorem. All right, so it allows us to make a list of all possible rational zeros of a polynomial function. All right. It doesn't tell you exactly which ones there are. It just says these are possible rational zeros. Okay. So if you have a polynomial function, has integer coefficients, you will have rational zeros of f in the form of p over q, p being a factor of the constant term, and q is a factor of the leading coefficient. So that means possible rational zeros is the ratio of the factors of the constant term over the factors of the leading coefficient. Okay, so this is what we need to know. We call these PRZs, or possible rational zeros. So if you want to list all of the PRZs, or possible rational zeros, you take the constant term. The factors of that are 1 times 4, 2 times 2. They could be positive or they can be negative. So we take the factors of the constant term. We divide them by the factors of the leading coefficient, in this case, 1 times 1. We look at positive and negative for all of those, and then you divide them. Now this one's easy because we're dividing by 1, so our possible rational zeros are 1 divided by 1 or 1, 2 divided by 1 is 2, 4 divided by 1 is 4, positive and negative for each of them. These are your possible rational zeros. All right, now if I actually show you the zeros of that polynomial function, here they are. You have 2 and negative 2 are the rational zeros. Are they on our list? They absolutely are, positive and negative 2. The other ones were just possible. They are not the actual zeros, but they are the zeros. Now, this is a degree 4. That means there should be 4 roots. I'm only seeing 2. What about those other 2? Well, you know what? For fun, let's find them. If I take this and I'm going to divide out a negative 1, then I can factor this. It's a trinomial. It factors into x squared and x squared. Factors of negative 4 that add to negative 3 would be negative 4 and 1. If I'm solving, I can divide by negative 1. It's still 0. This x squared minus 4 is a difference of perfect squares, so x plus and minus 2. X squared plus 1 cannot factor further, so that means I get x equals negative 2. There's that 0. X equals 2. There's that 0. Then I get x squared plus 1 equals 0, and if I solve this, I get 2 more roots, and they are positive and negative I. So 2 imaginaries that you don't see on the graph, right? We recall that. And then we have 2 real ones. All right, so let's list all the possible rational zeros here. So PRZs, positive and negative always. Factors of the constant term, so 1 and 2. Factors of the leading coefficient, 1, 3, 5, and 15. So our PRZs, this is going to be a bigger list, and I have to divide by all of these in the quotient. So 1 divided by 1, 1 divided by 3, 1 over 5, 1 over 15, and then go back through with the 2. 2 divided by 1, 2 divided by 3, by 5, and 15. So there's a lot more in this list. So it would take us a little bit of work, and that's why we have these next little theorems that we can use. So other tests for the zeros of polynomials. We have what we call Descartes. Okay, he was the one who discovered this and came up with it. So Descartes' rule of signs. So if we have our polynomial function with real coefficient, it says the number of positive real zeros is either equal to the number of variations in sign for f of x or less than that number by an even integer. Similarly, the number of negative real zeros is either equal to the number of sign variations in f of negative x or less than that by an even integer. So what does that mean here? If we have f of x, we look at the number of sign changes. So from 3x to the 7th to negative 2x to the 5th, there's one sign change. Negative followed by negative, no sign change, but then it goes negative 1 to 7, there's another sign change. Positive 7 to positive x, not a sign change, but positive x to negative 3, sign change. There are 3 sign changes for f of x. That means there are 3, or we decrease that by an even integer, 2, or I'm sorry, just decrease it by 2, so 1 positive real zeros. Why do we decrease it by 1 or 2? We decrease it by 2 because, remember, imaginary, we're talking these are positive real or negative real. If they're not real, they could be imaginary, and imaginary come in conjugate pairs. So this whole decreasing by an even integer is because imaginary roots come in pairs. So that's why we decrease by 2 each time. All right. We also would look at f of negative x and see how many sign changes. So let's actually do it for a problem here. So determine the possible number of positive and negative real zeros. So for f of x, how many sign changes do we have? We go from a positive to a positive to a positive to a positive. There are 0 sign changes. That means there are 0 positive real zeros. Well, what about for f of negative x? So f of negative x, if I put a negative into here and I cube it, that would be negative x cubed. 2x squared doesn't change because squaring a negative doesn't change it. Then it will be minus 5x because the negative in there, and the 4 is not going to change. So how many sign changes do we have this time? Negative 1 to positive 2. Positive 2 to negative 5. Negative 5 to 4. There are 3 sign changes. So that means there are 3 or 1 negative real zeros. Okay, which would make sense. If there are no positive real zeros, that means we'd have 3 negatives, or we'd have 1 and then 2 would be imaginary because we have to have three zeros as it is. All right, now the next piece is a little bit tricky, but we'll see what this means for us. Upper and lower bound rules, because we're talking about polynomial. You would only use these, A, when I ask you, or B, when you're not able to factor to find the zeros. So you need some other way to find them, okay? We've always given you stuff that was factorable in the past or given you enough information. This is now extending off of that. If we have f of x as a polynomial with real coefficients and a positive leading coefficient, so nothing new. If we divide by x minus c using synthetic, when c is greater than 0, so right here this is a positive, each number in the last row is either positive or 0, then c is an upper bound. I'll point that out as we go. If c is less than 0, the numbers in the last row are alternatively positive or negative, so they go back and forth. 0 counts as either one. Then c is a lower bound. Okay, so what does that mean? Let's check it out. So determine the real zeros. Your first thing would be like, all right, I'm going to set this equal to 0. Can I factor it? Answer is no. Grouping's not going to work. So then you're like, Miss Lynch, how do I find those roots? I know there's 3. How do I get them? So I would say use what we just went over. PRZs first. So what are the possible rational zeros? So factors of the constant term, 1, 2, 3, and 6, divided by factors of the leading coefficient, 1. So our PRZs are positive and negative, 1, 2, 3, and 6. Then we would use Descartes. We would look at f of x. How many sign changes do we have for f of x? It goes positive, positive. Oop, there's a negative. to a negative. So there is one sign change. That means there is one positive real zero. It might be on this list of 1, 2, 3, 6. It might be irrational, but there is one. Then I look at f of negative x. So f of negative x would change that first sign, not the x squared. It would change the 5x, but not the 6. So how many sign changes? Negative to a positive, 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 positive to negative. 2 sign changes. So there are 2 or 0 negative real zeros. So now we combine all of this information, the PRZs, with the what we know about positive and negative, and start checking. We take guesses. We take educated guesses, but we take a guess. Now, because this could have 0, I don't really want to start with negatives. I want to start with where I know there is one positive real 0. So let's just guess. I'm going to guess 2. I'm going to pick in the middle. We'll pick 2. So I write down, we do our division. We're going to divide it out and see if it divides in evenly or not. I don't need any placeholders, so let's go. Oh, bring down the 1. 2 times 1 is 2. Add, multiply, add. Woohoo, it worked out. All right, so I got lucky there. X equals 2 is a real 0. It is our positive real 0. So this means that x minus 2 times, this would be x squared plus 4x plus 3, equal that f of x. Or we want it to be equal to 0. So we know x equals 2 is one of our zeros, and it's the positive one. Now, this is a quadratic. I don't need to guess anymore. I can factor this or use quadratic formula if necessary. But this is factorable. 2 numbers that multiply to 3 that add to 4 would be 3 and 1. So that means I know x equals negative 3 and x equals negative 1. There are my 2 negative real zeros. So I have zeros of negative 3, negative 1, and 2. All right, so we used all of that information from what we just had to help us. Oh, this didn't load, so give me a second. I got to load that back up. Of course, it's going to go to the beginning. I'm deep in this packet. There we go. All right, so let's do this next one. Determine all of the zeros, again, using what we know of this function. So first thing, we'd set it equal to 0. Try factoring it. This looks like it would be factorable, but let's pretend it's not. Determine all of the zeros of this. So PRZs, we would go factors of the constant. So 1 and 2 divided by factors of 6, 1, 2, 3, and 6. So we'd get 1, 1/2, 1/3, 1/6, 2. 2 divided by 2 is 1 again, so I don't need to rewrite that. 2/3 and 1/3 again. I'm going to put them in order just because it's going to help when we do some guessing and checking. 1/3, 1/6 comes first, then 1/3, then 1/2, then 2/3, 1 and 2. Okay. Descartes, f of x, how many sign changes? Positive to a negative, to a positive, to a negative. 3 sign changes. So that means there are 3 or 1 positive real roots. How about for f of negative x? We would have a negative in the front, a negative for the x squared, a negative for the x term, and a negative on the 2. They're all negative, so there's no sign changes. So that means there are 0 negative real zeros. Okay, so that means negative is out. It's only the positives of all of those that are possible. So now we randomly pick. Now, because I don't really want to start with one of those fractions, I'm going to pick 1. So write it all out. No placeholders. Bring down the 6. Multiply and add. Okay, so X does not equal 1 because I didn't get 0 here. So 1 is off our list. But because these are all positive and I checked a positive, that means that X equals 1 is an upper bound, meaning it can't be anything past 1. So 2 is already out. All right, so now I just eliminated 2 of them by picking the 1. If I had picked like the 1/2 and it did that, I would eliminate 1/2, 2/3, the 1, and the 2. So it all depends on what you pick and if it's an upper bound or not. So let's try the 1/2. Let's see what 1/2 does. 6, -4, 3, -2. So multiply, add, multiply, add, oof, that's really 5 halves. Multiply, add, all right, so now, again, I didn't get 0, so it's not 1/2. And now these didn't all come out to be positives. So that means it's not an upper bound. So I should check greater than it. So let's go 2/3. I'm running out of a lot of room here, but let's do it. So multiply, that worked. Multiply, add, multiply, woohoo, there we go. So X does equal the 2/3. All right, then I know from here, if you remember from the division, because this would have been 3x minus 2, I'd have to divide by 3. This really makes it 2x squared plus 1, because if I divide 6 by 3 and 3 by 3, I would have 2x squared plus 1 that I can solve. It's not factorable, but I can subtract 1, divide by 2, take the square root, I'm going to get positive and negative 1 over radical 2, which I have to rationalize. So I get positive and negative radical 2 over 2. There's an I on those because I took the square root of a -1. So I get 2 imaginaries here and 1 real. So my roots are really, I'm going to write it up here. X equals 2/3, but then it also equals positive and negative radical 2 over 2i. So I have 1 positive real 0 and then 2 imaginaries which are not counted on there. All right, so these are big problems and you have to put all of the pieces together and all of the theorems, use them together.